Hello, my name is Rez, and I'm a professional game programmer, and I do electrical engineering as a hobby. Okay, I've been on this H-bridge kick for a while. We are on day 11, and we've gotten two transistors. And the reason why I kept saying things like, well, I think there's going to be a transistor behind this door, is because an H-bridge requires four transistors and often several diodes, depending on the type of transistor. A lot of times a MOSFET is used, and it may already have a diode internally. But a a bipolar H bridge is like four transistors, four diodes, a pile of resistors. I mean, it's not a super trivial circuit. So I kept thinking, oh, if they're going in this direction, which is the direction that I assumed we were going, that we'd have all these components. But I'm pretty sure now, after thinking about this, that there's no way that we're going to have the components to do it. So the question is, if we have a little robot, our little like boxy robot here, and we want this, we have wheels on this robot that are connected, and there's one on the other side, and we want the robot to go forward. How do we get this robot to turn? What do we do to get this robot to turn? Now, the easiest way, or at least I guess the common way, is that you have a motor here that's rotating like this, and you have a motor here on the other side that's going to rotate in the other direction. So they do that, right? They just rotate like that. And you kind of rotate on a point. That's the way that it is typically done. However, you could, especially if you have kind of a rubbery surface, it can stick to the surface with a decent amount of friction, you could just have this motor stop while this motor turns. That's a reasonable way to do it as well. You're not going to get as accurate, but it will turn, and it'll turn about that pivot point. So the nice thing, if I have a robot that's like this, just top down, the nice thing is that my pivot point is here. If they're counter rotating, it just rotates perfectly in place. If I don't do that, then my best case is that I've got my wheel sort of here, and I've got my wheel here. If I'm turning to the right, this actually becomes my pivot point, right? Because it has to rotate on that point, so it's going to do that. So it's going to rotate around like that, as opposed to rotating like that, if that makes sense. Um, it also is not necessarily exact, right? It's not going to rotate very well on, if it doesn't have a rubber surface on the wheel, for instance, or some kind of high friction surface. If I have it go, say, on my lab table, which is this relatively smooth white surface, I mean, it's not going to go. And we have this like glossy paper thing that they've given us for the track. So it's not going to go. So they have to have some kind of rubber thing on the road if this is the direction that they're going. The other option is they could actually give us two more with just a couple of resistors and a couple of transistors. You can kind of do a forward reverse thing. The problem is that you'd have to have an actual positive and negative. So they could do something like this, where you've got this, let's see if I can draw this. So you've got this point here, and you'd have to have this go into some transistor like that. This one is probably going to be your NPN. And then you've got another one that's coming on this side. You basically have a complementary circuit, but this one is PNP. So this goes the other way. And then these guys connect like this. And then this comes out to your motor. This, we're done here. The problem with this, and then this is the collector of this transistor. So this is your PNP, and this is your NPN. The transistors work similarly. I'll circle these because it's fun. The problem here is that this is your input. This is your plus voltage. This becomes your minus voltage. And you need to be able to have a signal that comes in, like positive versus negative. So if you get a positive value here, it means that we'll have this transistor will end up being able to conduct, because we'll have essentially a negative differential here that'll go in through here like that. This transistor will have a sort of negative differential here and a positive differential here, this will not allow it to conduct. It needs to go the other way around. So so this transistor will not conduct at all. This one will, allowing more current to flow through this junction. So the motor will conduct and it will go in that direction. If, however, we have like 0 volts here, then exactly the opposite will happen. And this with a negative voltage, this will be able to actually conduct. And so that's what's going to happen. That's one way of doing this, but we'd need to have a negative supply, and it gets complicated. So this book is a book called Practical Electronics for Inventors by Paul Schertz and Simon Monk. And this is a pretty good book. It's, most electrical engineering books walk the line. There are kind of two different types. There are engineering books that are like, something like this, which is really meant for a hobbyist. And so they're not going to go super deep into much. This is really just meant for hobbyists. So there's, you're not going to get a lot of the deep engineering stuff here. And then you have books like this, which are fairly hardcore books. I've shown this book before, right? And you get a lot of the deep math. It's rare that there are books that are in between those 2 points. Most books are either really solidly in the this is basically a textbook, or they're, really, really light on details. This book walks the line between them quite well. It doesn't shy away from the math, but it also doesn't go super deep into stuff. So if you're looking at getting into engineering and you want to get started with some, electrical engineering stuff and want to go beyond the basics, this is a good bridge to that, I think. Start with a book that's fairly basic, that doesn't go into a lot of huge details. Maybe it talks about Ohm's law and stuff like that. But then this is a good second book. It's organized a little wonky, but it doesn't get away. It doesn't shy away from the math, which I think that's the folly of a lot of books. Enough of the selling on this book. If we go a bit further, we can actually see what the H-bridge circuit looks like. So this is the bipolar one. This is the one this is the direction I thought we were potentially going in. So we have our forward bias here and our reverse bias here. So we basically get 2 inputs into this circuit. One for reverse, one for forward. So if you put a signal on the forward pin, basically, then the motor's going to go forward. If you put it on the reverse pin, the motor's going to go reverse. Basically what happens is we bias this transistor, which allows this to flow through this collector. We have in this case, I have a 12 volt supply. The supply doesn't matter overly in this case. You have to tweak these values, of course, but it doesn't matter overly. This allows power to flow through this motor. In particular, it goes through, where am I? This PNP and this NPN, right? So it's going to do this sort of thing. And it does the reverse over here if you put a reverse voltage here. So it allows the motor to turn in both directions using these voltages. Now, typically you have what's called a PWM speed control. PWM stands for pulse width modulated. It just means that you're just pulsing it, as opposed to having a constant voltage. You can pulse the voltage. It's a better way to get speed controls. Now, you can build this yourself, and it's a reasonable way to do it, but you can also get something like this. This is an H-bridge. That's all this is. The transistors, the MOSFETs, are in this chip, and for a decently powered motor where you want to crank a lot of power into it, those MOSFETs are going to pull a lot of energy. And so that's why it has a heat sink on it. So the MOSFETs are all in here, and they have this heat sink here, and we can see the various different pieces. And that's it. So I will see you all tomorrow.